All right, we're going to look at differential equations with exponential functions. So this is part one. Now, before we get carried away, let's just remind you of what exponential functions are like. So they would be functions like, oops, my pen isn't working, there it is. So you might have y equals 2 to the x, or you might have y equals 3 to the x. Or maybe you have y equals 10 times 7 to the 4x. So all these are examples of exponential functions because we have our variable as an exponent. Now, in the calculus world, we choose a particular base which is superior than the 2, the 3, or the 7 that I wrote down here. We prefer to use e. So that's the base of choice for calculus, or a more generalized version of it. I maybe change colors. So this is our basic format of exponential functions that we prefer to work with in calculus. Some kind of constant could be out in front, and then we want the base to be e, and there could be some number multiplying the x. Okay, like over here I had the 4 times the x. So this is your basic form of an exponential function that we want to study today. All right. So what is interesting about these things is if we do the following. So we're going to take this little fella here. Actually, let's go to blue in color. And I take a look at the derivative. Okay, so that would be c times the derivative of e to the kx. So that would be e to the kx again times k. Now you'll notice that c times e to the kx, that's all exactly the same thing as y. So I'm going to switch this out and write it like this. So the derivative is just k times the original function y. Now a way to understand this is that this rate of growth, which is what the derivative represents, so the growth rate is proportional to the function itself. So is proportional to the function. So the original function, that is. Okay, so in other words, it's like if you took the original function, you times it by 1/2 or something, that's giving you the growth rate. Now, to try to solve these differential equations, what we're really after is, actually, I'll just point to it up here. What is c? What number is c? And what number is k? Because e, we know what e is, and x is a variable, and y is the function. So it really boils down to c and k. So I'm going to do one example of that, and then that's probably all I'm going to do for this first introduction. Oops. Let's see if I got the right thing here. Okay, so one example. So we're going to tell you the following, given that the derivative is equal to 15 times y, and give you a little bit more information that y of 0 is equal to 8, we are going to solve this differential equation. So meaning this y prime equals 15y, so we're going to go ahead and solve that. Now, as soon as you see this y prime equals a number times y, that tells us that this must belong to this particular family of functions. Okay, so now what I can do is say, well, if it's this family of functions, I also know that y prime is equal to some constant times the function itself. So when I look at this, I immediately know, without doing a lot of work, that k is 15. So now I can take a look at this particular function here, and I can replace the k with 15. So I've got half the stuff figured out because I recognized y prime equals 15, y belongs to this kind of family of functions. Now I'm going to use this other information and plug in when x is 0, the function has to equal 8. Try and narrow down what c is. So if we put in a 0 for x, then we're able to narrow down that we have c times, now this is e to the 0, and anything to the 0 is 1. So c equals 8. So what is my final answer when I put it all together? Y equals 8 times e to the 15x. And that is my solution to this differential equation. And that's where we're going to stop for now, and we're going to come back with a little bit more twists and turns and more practical applications later on.